Alright, welcome back everyone. In this video, we're going to continue our design. We're going to continue our, it's not a design, sorry. We're still trying to figure out the profile, the temperature profile in our double pane windows. Okay, so we have, just to give you guys a quick recap, we have glass. Alright, we have glass, we have, let's switch colors, my bad. We have starting off with glass at x equals 0, then after some width we have an air gap, and we also have glass on the inside. All right, outside is at x equals 0 and inside is greater than x equals 3L. All right, very good. So at this point I have my equations for my three domains. Okay, my domain 1, which is the outside glass, the domain 2, which is the air gap, and domain 3, which is the inside glass. All right, so now there, as you can see, there are 1 2 3 4 5 6 constants of integration, which means I'm going to need 6 boundary conditions. So in this video I'm going to fully specify this problem. So let's see what's going to be our first boundary condition. Our first boundary condition was specified in the problem at x equals 0. The temperature at x equals 0, T sub 1, the temperature in the first domain. Keep that in mind. The temperature sub 1, sub is referring to the domain, at x equals 0 is equal to T out. Okay, so that's my first boundary condition. Temperature at x equals 0 is equal to T sub 1. Let's why don't we color code this one as well? Okay, so this one's going to be in blue. T sub 1 at x equals 0 shall be equal to T out. Okay, that makes perfect sense. That's a very simple Dirichlet boundary condition. I've specified the value. I've been given the value of my dependent variable at the boundary. Next up, I need my next boundary condition. So in order to keep track of your boundary conditions, you have to physically look at the picture. All right, let's see. At x equals 0, if we start moving, where's the next boundary that we encounter? We encounter this boundary at x equals L. Keep in mind, L is the width. L is the width of each of these domains. Okay, L is the thickness of each of these domains. My bad. So at L equals L, remember we had a perfect contact assumption. We had a perfect contact assumption. And what does that imply? Perfect contact assumption. All right, that means that the temperature profile is continuous. That means the temperature profile is continuous. What does that mean in English? That just means that temperature in the first domain at x equals L has to equal the temperature in the second domain. Okay, perfect contact assumption, perfect contact. There is no contact resistance. Okay, I'm gonna link in the description. All right, in my bibliography, the chapter which covers contact resistances in a heat transfer textbook. So all right, assuming perfect contact once again, perfect contact, I'm just gonna scribble that now. The next key assumption is going to be that the rate of heat transfer, the rate of heat flux from the first domain, kg times the derivative at x equals L, has to equal the flux that is going towards the flux into the next domain, which is the second domain. Okay, and there's a negative sign on both sides, but it's gonna drop out, so I'm just gonna not worry about it. Okay, it does exist though. All right, it does exist. All right, good. Sorry about that. Boundary condition 3. Okay, next up, our next boundary, as we keep moving into our problem, our next boundary is at x equals 2L. And using the perfect contact assumption, once again, I'll get two more equations. As you guys can probably look ahead. If not, then I'll just show you anyway. So you assuming perfect contact twice more, assuming perfect contact at x equals 2L, you'll be left with the temperature of the second domain at x equals 2L is once again gonna be equal to the temperature in the adjacent domain, in the third domain at x equals 2L. Perfect contact, so the temperature profile has to be continuous. There cannot be disjoint temperature profile. There cannot be a disjoint temperature profile. And boundary condition 5, assuming perfect contact again. Perfect. Scribble that. This is perfect contact. Okay, good. Contact, good. Now the flux expression. Let's zoom out a little bit. The flux expression. Ka. The derivative in the second domain evaluated at x equals 2L is gonna equal the flux expression evaluated for the third domain at the same value of x equals 2L. Okay, so all right, and my final boundary condition is gonna be at the temperature that's been specified at x equals 3L. And if you guys remember the problem statement, I said that temperature of the third domain at x equals 3L is held constant at T sub in. Okay, refer to the previous video, okay, for the description, and you can find that in the info that I provided with the problem. So my final boundary condition is just going to be T3 at x equals 3L is gonna equal another nice Dirichlet boundary condition. Very good. So okay, I have 6 equations, 6 unknowns. Oh boy, 6 equations, 6 unknowns. Oh my god, what a mess. 6 equations, 6 unknowns. They're all going to be, since I have Dirichlet boundary conditions in this case, they're all going to be linear equations. So they're all going to be 6 linear algebraic equations. Okay, linear algebraic equations, which means if you're so inclined, you can use tools from linear algebra if you're so inclined. But I'm not really going to do that. There's got to be an easier way to deal with all of this crap. The assumptions that I've made, let me go back and revisit my assumptions for a second. Okay, my assumptions are steady state. Okay, these are the assumptions: steady state, constant conductivity, no bulk motion, conduction, perfect contacts. We dealt with that. This gave us our boundary conditions. This gave us a total of 4 boundary conditions. Boundary condition 2 till boundary condition 5, okay? One directional transport. There's got to be an easier way. And turns out there is. And that's going to be my segue into the next video. The next video is going to be, just to give you guys a hint, we're going to use the analogy. Between heat transfer. Okay, we're going to use the analogy between heat transfer and current. Okay, current is the flow of charge. We're going to be using the analogy between these two seemingly distinct topics in physics and sciences. Okay, physics and engineering sciences. So if there's any, in the next video, we're going to see if we can use some analogy between these two subjects. Seemingly distinct subjects, but we'll see if we can come up with a phenomena. If the behavior at if the equations that describe both behaviors can be, that is, the structure of the equations can be at a higher level, we can use some analogy and maybe we can reformulate. We are going to reformulate this problem. Okay, we will reformulate this entire problem hopefully in a much simpler way. And in that way, hopefully we won't have to deal with a lot of linear algebra. And once again, this problem is fully specified. You can use tools from linear algebra, you can use MATLAB, whatever tool that you fancy to go crazy. However, we're not done. All right, I'll see you guys in the next part of this video. All right, thank you so much for watching.